Hi, welcome to part 2 of the derivation of the electromagnetic wave equation following Maxwell's laws. Now, in part 1, I worked out how we get the two breadcrumbs that we need in order to be able to show that electric and magnetic fields have to be the solution to a wave equation. Specifically, the partial derivative of electric field with respect to our location x has to be equal to minus the partial derivative of the magnetic field with respect to time, and the partial derivative of magnetic field with respect to x has to equal minus mu naught times epsilon naught, the permeability of free space times the permittivity of free space, times the partial derivative of the electric field with respect to time. So, to find a wave equation, what I'm going to do is take breadcrumb 1 and take the derivative of that with respect to x, or really take the partial derivative of that with respect to x. So on the left-hand side, taking two partial derivatives just means I have the second partial derivative of the electric field with respect to x. Pretty straightforward. On the other side, I would have minus the partial derivative with respect to x times the partial derivative with respect to time of my magnetic field. And the neat thing from partial derivatives in Calc 3 that you learn is the order in which they're processed doesn't matter. You can calculate this in any order you want. So I'm going to flip my order of differentiation. So I would still be looking at the partial derivative squared of the electric field with respect to x, and that would be equal to minus the partial derivative with respect to t of the partial derivative of the magnetic field with respect to x, which is breadcrumb 2. So minus times a minus gives me a plus sign. My mu naught, epsilon naught are constants, so they hang out front. And then I would have the partial derivative with respect to time of the partial derivative of the electric field with respect to time. That's a second partial derivative with respect to time for my exact same field. So this is a wave equation from differential equations. And the solution to an equation where the second partial derivative with respect to position equals the second partial derivative with respect to time times some constants out in front is a solution of the form of an amplitude, which here would be our maximum electric field, times the cosine of kx minus omega t. Now I could add in some arbitrary phase angle plus phi. I could use a sine instead of a cosine. Both of those work. They're both ways of writing out a wave equation. K is our wave number, 2 pi divided by the length of our wave, and omega is the angular frequency of our wave. 2 pi times our regular frequency in hertz, 1 over the period. Now, this term right here, mu naught over epsilon naught, that is 1 over the speed of the wave squared. And since we're talking about electromagnetic waves, which is light, that is 1 over the speed of light squared. So the speed of light is written into Maxwell's equations. Literally, it's 1 over the square root of mu naught times epsilon naught. So if you take 4 pi times 10 to the negative 7 Tesla meters per amp, multiply by 8.85 times 10 to the negative 12 farads per meter, multiply them, take the square root, invert that, you get the speed of light of 299,792,458 meters per second. Right out of the Ampere-Maxwell contribution plus Faraday's law smushed together. Now, that's not the only way you could do this. You could take the derivative of the magnetic field with respect to x. Calculate that second partial derivative, do the same process up here with the e dt, make use of this, you end up with the exact same wave equation, only E becomes B. So what we would see with the magnetic field would be a magnetic field as a function of space and time that's equal to a maximum magnetic field times our exact same wave function, cosine of kx minus omega t, exact same speed. And it also turns out that our magnetic and electric field amplitudes for plane waves are linked to each other. The maximum magnetic field is going to be the maximum electric field divided by the speed of light. Thanks for watching.